There we go. Okay, so we talked on Wednesday. Let's see, oops, I gotta push more buttons, don't I? Let's see if technology works. Technology's not been my friend. No, no, no. There we go. No, they weren't ours.
Yeah.
That technology was, well, the problem going to Stillwater and Enid were ours, but not what we had accomplished elsewhere. Okay, so this is, okay. All right. Let's see what we got. Can you guys see the screen over there in Enid?
Yeah.
Okay, cool. Okay. So we had talked on Monday about this, that if I have a plane, this is my velocity vector, this is my magnetic field vector, this is going to be my force vector, and we could do the right-hand rule, and that would give me that the magnitude of the force was going to equal Q, V, B, sine theta. Key here is, if you remember, the magnitude of the force for an electric field is just QE, but with the magnetic field, we get an extra term, or an extra term. See, I told you, I'm not 100%. So we get that, and this results from the cross product. Okay, this is coming from the cross product, is where we end up with that we have to worry about it. And that means that the velocity vector has to be crossed into the magnetic field. Because remember, cross products are direction sensitive. Okay? They are direction sensitive. And we also talked about that if I do things like this, that comes out of the paper, these things go into the paper. And we end up having things work out. So that's where we ended on Monday. That's where we kind of stuck with it and we ended on Monday. So if I've given a magnetic field and we're going to be directed into the paper, and I'm going to put a positive charge in here. And it's our test charge. And we're going to have our charge move that direction. Okay? So I'm going to take my velocity, and I'm going to take my velocity, angling it into the paper. So I'm going to line up with the velocity. My things are going into the paper. It ends up that my force is going to be in that direction. Okay? And you can play with your right-hand rule and make sure that we get it, that my force ends up. And now you understand, by the way, chirality is important. That is the one thing we did get out of last night. Chirality is important. Right hand versus left hand makes a big, huge difference in a lot of things. It makes a big, huge difference with magnetic fields. So chirality is important. So we get that, and my test charge does go this direction, so my force goes here. We've seen this before. Right? We've seen this before. If I have something that hits my planet, and I bring in something with a velocity as it goes through the planet, or goes around the planet, what happens is I curve and I slingshot off on the other direction because I have a force that's center seeking. Okay? I have a force that's center seeking. So we've seen this before. Right? So what's going to happen to our lovely little charged particle is it's going to start going this way, and in fact what we end up seeing is it ends up doing something that looks like this if my magnetic field is going in this direction. We get helical motion, okay? So it doesn't stop, it's not going to stop and stay in a curve, but we are going to get a curve in there, and we are going to be center seeking, and it's just a matter of whether I have a positive or negative charge, whether my charge goes this way through the field or my charge goes this way through the field.
So it's going to be on top of itself in a circle?
Well, if I'm going negative, it's going to, yeah, it'll be on top of itself, but we're going to be traveling in a circle into the page with a positive charge.
Okay.
If I have a negative charge, we would be traveling in a circle out of the page with a negative charge. Because remember, I'm going in two different directions if I have a positive or a negative. Okay? So we've seen this before in centripetal motion. So if I look at my force, magnitude of my force, since I'm perpendicular, that's the magnitude of the force. It's the velocity of the particle times its charge times the strength of the magnetic field. But this is, since it's a centripetal acceleration, it can also be mv squared over r, because that's my centripetal acceleration. And if we solve for r, right, we're going to solve for r. The reason we're going to solve for r is because it's important. Because I said so. I just feel like that, you know, that's the way it is today, right? So I get r is equal to mv squared qvb, and this is got a special name. This is like our cyclotron radius. It's a cyclotron radius, and if I look at it in terms of omega, I end up with 2 pi, the period of the circle. Right? That's the period of the circle, and this becomes what we call the cyclotron frequency. So we have a cyclotron radius and a cyclotron frequency, and those things were useful if you play in the high energy world. They're very, very useful, because that's going to give us the size of our accelerators. Okay, that's going to give us the size of the rings of our accelerators, and those are big rings, by the way. Those, you know, like one in argon, I think it's got a radius of a mile. I don't know what CERN has, and I don't know what the other ones have, but it's important there. But we get, and then omega. If I look at omega, omega is v over r, and if we talk about that, omega actually calculates out to be qbm when I play with the mathematics. I can get QBM. Those are my cyclotron frequencies. Those are my cyclotron radii. But we can actually use this for other things. We can use this for analysis. Everybody's watched CSI, right? And the two instruments they use at CSI all the time are what? They want to detect the substance. Now they go find the substance, they have no idea what it is, and they end up putting it in the what? Well, they always centrifuge everything. You centrifuge the sample all the time. Centrifuge concentrates the sample. They put it in some kind of spectrometer. That's getting, what kind of spectrometer? What did you say, gas? They do a mass spectrometer is one, and they go do a gas spectrometer. Usually what happens is they will do a GCMS, okay? That's usually what they're going to use, because that's important. Okay? They usually use, that's what they said, they're going to put it into a GCMS. This means it's a gas chromatograph on the front end. And on the back end is a mass spectrometer. So we have the gas, and what happens with the gas spectrometer, or the gas chromatograph, is I'm going to separate the analytes by their time in the column. So they're going to come off. So things with the same residence time are going to come off together, and they're going to be eluted from the gas chromatograph, and then they're going to hit a magnetic field. Okay? They're going to hit a magnetic field, which is going to cause them, essentially, to go into a circle and hit a target. And we just saw that my radius is dependent upon the velocity and the mass. I know what the charge is because I can make it have the charge I have. I know what the magnetic field is because I can set it. So basically, all I got to worry about is what the radius is of the way the little ion went when it hits the detector. So that's how we actually can tell the different masses, because different masses are going to hit the detector in different places. So it works pretty cool. So those are very important. Okay? So we know what happens if we're parallel. What happens if we're parallel, we get 0. What happens if we're perpendicular, we get a nice curve and it's going to be in a helical pattern. What really gets us is when we're not in perpendicular or parallel. Now, a lot of times when we build devices and when we set things up, we get to choose and we get to make it that way, but we don't. Now, remember way back when we talked about doing something that looked like this? We defined this little critter, right? We defined this little critter, and the first definition we talked about it as a divergence. Okay? Talked about it as a divergence. This little critter, and that's when we do the dot product with it. That's my divergence. And then I warned you that we were going to play with this when it's the cross product, and this is called the curl. So we end up with a curl, and remember this stands for the derivative with respect to x in the I direction, plus the derivative with respect to y in the j direction, plus the derivative with respect to z in the k direction. Now the curl becomes a lot easier to play with, okay? Curl becomes a lot easier to play with, and we can get it. But the big issue here is we're wanting to end up with a variety of different things, but we will see the curl come into play. So that means that if I'm doing my cross products, just to remind you about cross products. So if I'm doing F B is equal to Q V cross B, FB, if I do this, is going to look like Q, I, J, K. And if I only have a velocity in the V, and the X and the Y, it's going to look like this. And my magnetic fields in the X direction, it's going to look like that. And we can do the determinant of that lovely cross product. Okay? What that ends up doing is going to give you your right-hand rule mathematically. And this will end up being, if I do this, I end up with minus Q, V, Y, B in the K direction. If my velocity is in the XY plane, has no K, but now you see that the force actually pushes it in the K direction. And this is Vy. And if I do my Vy, and I can show you, this is also where you get your sine of your angle thingy, my love. Because if I go back and I look at it, I can put my sine of my angle in there. So mathematically, we could play with a lot of different things, and we will start to see the curl, and the curl becomes important. And we get a helical motion. Okay, let's see how I want to do this next part. And we'll just dive in. Because I would probably muddle it up anyway. So we're going to start with what's known as this lovely thing. I'm going to be working with this peachy dandy thing. And if we do this, the magnetic field is going to be some constant. We happen to know it's my permittivity of space divided by 4 pi. My charge, and it's going to be the velocity crossed with r like this. And this is for a point charge. This is the Biot-Savart law for a single charged particle in a magnetic field for a point charge. And remember, if I just do any two vectors, cross any two vectors, it's going to be A, B, sine of the angle. So if I do V cross R, I'm going to get V R sine of the angle. And I'm going to plug that lovely back in. But this is going to be in my R unit vector in the R direction. And I end up with U cubed 4 pi V sine R over R squared. It's another way of looking at what we already have figured out. Some key things, and what you're going to find is, depending on what book you're using, depends on what constant they put in front. Because remember that the constants, like permittivity of free space and this, are actually related to each other. So you may see it differently. And I'm going to tell you where we're headed. Where we're headed is to get Maxwell's laws, or Maxwell's equations. And there are 4 of them. But what we're going to see when we get there is Maxwell's correction to account for time and motion in the magnetic field. Because basically what was happening goes back to the fact that everybody was doing all of these empirical experiments and things weren't quite working out right. They were on the right track, things were doing okay. We saw the comparison between electric fields and magnetic fields. There were certain things that are the same, and now there are certain things that are different because I get motion in the magnetic field that I wasn't getting in the electric field. I've got a circular path now that I have to worry about. I got a cross product that I have to worry about. None of that was happening in the electric field side, but it was happening in the magnetic field side. And we're going to end up with Maxwell's equations. And if you go pick up different books, you're going to see different forms of Maxwell's equations. So we've got to kind of keep track of what those forms of those Maxwell's equations are. And then we all get to feel dumb because Maxwell solved it on his entrance exams into Edinburgh, which is a real pain in the tushy. Because he goes, oh, this is what you got to do to fix it. And he was right. It's kind of a bummer, but he thought that way. Okay? But the key here is magnetic fields, electric fields, and gravitational fields all are proportional to 1 over r squared. So when you get ready to take your GREs, when you get ready to take your Ps, remember these things are going to diminish as 1 over r squared. So that actually is a helpful way to figure out your test questions. If they're multiple choice, goes off as 1 over r squared. Very, very helpful. Mu, this mu right here, is the permittivity of free space, and it happens to be 4 pi times 10 to the minus 7, and the units are Tesla, meter, amperes. Okay, we're just gonna talk theoretical here. Because I don't want to try and mess this up, because I will mess it up today. Okay, so this is for a single particle. All right? This is for a single particle. Where we're gonna get to on Friday, and hopefully I will be cognizant enough to be able to do it on Friday. But if we think of a wire, so I got a wire, and this is my point charge. 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 We can look at my wire as a series of point charges. We also can look at it, if my point charges are in a wire, I get a velocity, right? Isn't that how we define current? So I can look at a section of my wire as the current flowing through the wire times its independent little length. So what we're actually going to be able to do is write the Biot-Savart law for wires. See if I can get it. I have it in my notes here. Yeah. We can actually write force for my magnetic field is going to be the current times the length of the wire, magnetic field, sine of theta. So we can get rid of Q and its velocity. And we can actually look at it in terms of current in the wire and the length, which means if I want to know the magnetic field around a wire, so here's my wire, it's coming out of the page, okay? I lay my thumb along my wire and my fingers are going to give me the idea of how the forces are going to come together for my magnetic field. And if we look at it from Ørsted's point of view, and so a lot of times you'll see a wire written like that, that's a wire coming out of the page. If I put my little compasses around here, Ørsted actually showed that my compass needles are going to move, and I'm going to get things around the wire. So I'm going to get my things floating around the wire, and my right-hand rule is going to tell me how that works. So I can actually get there. Which means I can start looking at wires. If I have current going in these two directions, if I do my right-hand rule, things are going to come out of the page here and go into the page here for this wire. But for this wire, I'm coming out of the page and I'm going into the page. So there's going to be a place between these two wires that things are going to cancel each other out. Conversely, if I do wires that go like this time, this is going into the page over here, coming out of the page over here. Guess what? These are coming out of the page here, and these are going into the page over here. I'm going to be able to use this condition to create, if I have loops of wire, which is the lab you guys are going to do today. You get to use a slinky as a solenoid. You get to create an electromagnet, and you get to create a magnetic field inside the slinky. And it turns out my magnetic field becomes dependent upon how many turns that I have in my wire and these things are adding together, and I get a nice uniform electric field, and this is a solenoid.
I think we already did that one.
We did that one like 3 weeks ago, I think.
What, the magnetic field in a slinky?
Yeah.
Okay. We haven't done it over there on the unit side yet. That's the one we're doing on Friday.
Yeah, we're like really at. And it's kind of confusing because we don't
We learned the concept there, and then, I mean.
Well, this, in this
why
case
we
for,
did it, and then we learned-
yeah, but in this case for magnetic fields, that's a good thing. That's a good thing. But that's your solenoid. Now, it's a kind of a toss-up, which way's best. And there's a big debate in physics, whether or not we have you do the experiment first and then teach you the theory, or do the theory and then let you do the experiment. And it's about a 50-50 mix which way we sit there and look at it and say which way's best. When it comes to magnetic fields, this way's best, folks. This way's best. You guys do it in lab and then figure it out in class, because the mathematics gets a little, they really were, I kid you not, they were developing the mathematics to explain what they saw. They were really developing the mathematics to explain what they saw. The math and the observations were going hand in hand for calculus. They were going hand in hand. So you get your solenoid. So you guys are starting optics then.
Yeah, that's right. I thought we were doing the pinhole camera today.
No, pinhole camera, you're not going to be able to do the pinhole camera today. That's your final project. It's kind of like the A-drop project. Yeah, no, you can't do, well, you can. I can make a pinhole camera pretty quickly. I can usually do that without any trouble.
What's your price?
Huh?
What's your price? I need a good final in that class.
Pinhole cameras are easy to make. Explaining them is a different story, and getting a good image is a totally different story. But they're super easy to make. In fact, I can do one right now. If somebody's got a straight pin.
what?
Straight pin. You get a straight pin, or in fact, all it takes to make a pinhole camera is to have a nice sharp edged hole in your piece, and that will become your pinhole camera. And in fact, for solar observations, that's exactly all you need, is a piece of cardboard with a nice sharp point, a hole through it, and then your floor is your base. So it doesn't take much for pinhole cameras. The trick is being able to capture the image. That's the trick. Trick's also being able to focus the image. That's the trick. Making the camera is simple. In fact, they knew about it all the way back to the Greeks. It was whether or not you could record the image that was the problem. So if you guys are starting optics, you guys are going to do reflection and refraction, and that's where the other piece. Okay, so one of the other things that we got to worry about, so we know it because we've been seeing the images, right? That a current's going to generate an electric field, and my electric field is going to, or current's going to generate a magnetic field, and my magnetic field can generate a current. And it's the changing magnetic field that generates the current, okay? Keep that in mind. It's the changing magnetic field that generates the current. So what we end up with is this. So if I've got a magnet sitting out here, and I have, and we end up, see if I can draw it in here nice and pretty. So I get a loop of wire in here. So I've got a loop of wire inside my magnets. And now I do a current on there. If I apply a current, okay, I'm going to apply a current in this case. If I apply a current to that, I'm going to generate a magnetic field, right? Magnetic field may or may not respond well to the magnetic field that I've got inside my magnet, and I can actually get this loop to turn. That is a simple motor. And those are easy. You can buy them at Hobby Lobby. We have a whole bunch of them. I never can seem to get them to work because it's a pain in the tushy. But I could put my C battery in here, and these are conducting copper strips, and I have a loop of wire. I have multiple strings of wire across here. And as long as I have scraped off the insulation on this wire at this point, and I have a little magnet right there, I can start that sucker and I can get it to turn and I can get it to spin. And as long as I have current, it's going to spin. Or what usually happens with these little gizmos is that it moves enough that you end up in a spot of the insulated wire and it doesn't get current in the loop anymore and it stops. The other problem is you got to have the loop just so it doesn't hit the little magnet, so it doesn't stop just because it hits the little magnet. So that's why these things frustrate me all the time. But I can get it, and that's an electric motor. Okay, that's an electric motor. Your car does have a motor, by the way, but it is not the engine. It is an internal combustion engine unless you have a Prius and you actually do have an electric motor. Now I can't say that with as much conviction as I used to be able to. I hate it when people say the motor. Well, the motor is a specific part of the engine, and the engine is an internal combustion engine. Okay, two different things. Your car also has something that's called the alternator, and the alternator is essentially a generator. Okay, so in this case, we apply the current. The current is going to cause the interaction between the magnets, which is going to cause the motion. Generator's a little different, okay? Generator's a little different. I've got a loop. I've got the same loop inside here. Okay, I got the same loop inside, except now I'm going to apply mechanical force on this, such as water falling off of a water wheel, or steam hitting fans in a turbine. But we're going to generate this, which is we're going to use mechanical means to create still magnetic field. Okay, I still got two magnets out here, still magnetic field. But I'm going to start moving my wire. Magnetic field generates current, right? Magnetic field, moving magnet, and I'm in motion, and I end up getting current out. The difference between an AC and a DC motor is how you have the pickups on this loop. And the DC motor will give you this, or the DC generator will give you current that looks like this. My AC will give you current that looks like that. So that's how we actually pick it up. I will be giving you guys a homework set for motors and generators, and that's all we'll be focused on is motors and generators. Because one of the agreements that we have all made between all of the different institutions is that you have seen motors and generators in Physics 2. We just don't have time to sit and spend a whole lot of time on them. But it comes from the fact that what we've got is that a current in a wire generates a magnetic field. A changing magnetic field generates a current. And that's called induction. And so it's an induced current. It's an induced current. And I'm going to stop there because I'm not diving into something else today. Monday, we will not have class. Remember that. Monday, we will not have class.